Good morning, Algebra 2 students. Welcome to video 1 of week 2 of online learning. This is Miss Bendon. Miss Mansour and I miss you. Last week we talked about angles and we talked about them on graphs. We said that now we're putting them on the XY plane here and they are in standard position. If we have an angle that has its initial ray here along the x-axis, its vertex on the origin, and its terminal ray here coming out from there as well. And then we talked about coterminal angles. What is a set of coterminal angles? Cool. So coterminal angles are angles that share the same initial ray and terminal ray. So what is a coterminal angle of 135 degrees? Well, the easiest one to spot is this angle 135 degrees is going clockwise from the initial ray to the terminal ray. So that is a positive angle. But we could also go, wait, did I say clockwise? I meant counterclockwise. We could also go clockwise the other way around. And because we're going clockwise, that is now a negative angle, but it's going from the same initial ray to the same terminal ray. So it is a coterminal angle of positive 135 degrees. So let's figure out what angle that is. We know that this whole piece together makes a circle, and a circle is going to be 360 degrees. And then our negative angle here is taking up the entire portion of the circle that is not that 135. So let's get rid of that 135, and what's left to be our circle is 225 degrees. But again, that's a negative direction, so it's negative 225 degrees. So negative 225 degrees is a coterminal angle of 135 degrees. But it's not the only coterminal angle, and I'm going to erase this, and we're going to start to make a list. I'm going to draw another one on here. So let's do another positive one. I'm going to start at this initial ray. I'm going to come around. I'm actually going to go past that terminal ray back a full 365 degrees, and then I'm going to keep going and stop at that terminal ray. So I still started at the initial ray and ended at the terminal ray. It is therefore a coterminal angle, but it is that full 360 degrees of the circle plus another 135 degrees. So that's 495 degrees. And we can say that 495 degrees is another coterminal angle of 135 degrees. And I could keep doing that as many times as I wanted. I could circle around twice, and that would give me 720 plus 135 is 855 degrees is another coterminal angle, and I could keep adding circles indefinitely. There are an infinite number of coterminal angles, and we could still do the same thing going in that clockwise negative direction. So I could draw a negative angle that started at that initial ray, circled around once, and ended at the terminal ray. And that's still a full 360-degree circle, plus that 225 degrees that we have to travel clockwise to get to the terminal ray. So that is 585, but because it's clockwise, it is a negative angle. So it is negative 585 degrees, and we could keep adding additional circles around to that. So lots of coterminal angles. I don't need to. Similar question, what is a coterminal angle of pi over 3 radians? And last week we talked about radians as another unit that we can measure angles in instead of degrees. And we're going to do the same kind of math to find coterminal angles of pi over 3 radians. We have a positive angle here because it is going counterclockwise from the initial ray. So let's start with the same easiest one to spot of going counterclockwise or clockwise. I don't know why I can't keep track of these today. I'm sorry. We're going clockwise for a negative angle. And we're going to do the same math that we did before. When we did this for 135 degrees, we knew that this full circle was 360, and then we subtracted the portion we'd already done. How many radians are in a full circle? Great, 2 pi radians make up a whole circle, just like 360 degrees makes up a full circle. So we're going to do 2 pi radians minus pi over 3. And you could put 2 pi minus pi over 3 into your calculator, but you will get a big long decimal answer that is rounded, and we would rather leave our radians in terms of pi. We want to leave that pi symbol in there. So what we're going to do instead is we're just going to subtract the fractions, and we can think of 2 pi as 2 pi over 1. And in order to subtract fractions, they have to have the same denominator, but our denominators are 1 and 3, and that's pretty painless. We can just take this fraction and multiply it by 3 over 3. 3 divided by 3 is 1, so I'm really just multiplying it by 1. I'm not changing the value at all. But 3 times 2 pi is 6 pi over 3 times 1 is 3. And then we've got 6 pi over 3 minus pi over 3. And now that we've got that, we're just doing 6 pi minus pi on the top is 5 pi. So this negative angle going around is going 5 pi radians over 3 rather, but because we're going clockwise, it is negative. So negative 5 pi over 3 is a coterminal angle of pi over 3. And we can do the same going around the circle more than once trick to find other coterminal angles. We could say if we're going now in the positive direction, we could circle around once and then, oops, I went too far. We could circle around once and then stop at that coterminal ray and have another angle that is coterminal to pi over 3. And when we did that with degrees, we just did 360 plus the angle. We're going to do the same thing here, except it's going to be 2 pi plus pi over 3. And we already did this math. We can convert 2 pi by multiplying by 3 over 3. And it's 6 pi over 3 plus a pi over 3 is 7 pi over 3 is another coterminal angle of pi over 3. So radians, not super painful, right? Just a little bit more fractiony. Some pi. Who doesn't like pi? All right, guys, quick check-in for coterminal angles. What is a coterminal angle of 50 degrees? Bonus points in my heart if you can list more than one. Lots of options. You could have gone negative around the circle and I clockwise direction and gotten negative 310 degrees. You could have added another 360 degrees on and gotten 410 degrees, and you could have kept going like that to get 770 degrees. All right. So then you also last week reviewed some of the trig ratios. So we're going to start with sine, cosine, tangent. And really quickly, I just want to check in and make sure that you know, oops, that's the wrong diagram. Okay, fixed it. That you know how to find the sine, cosine, and tangent of angles on your calculator, whether they are given in radians or degrees. So the first thing you should know is that we have to tell our calculator before we put in sine, cosine, and tangent functions whether we are putting them in measured in radians or degrees. So pick up your TI-84 and hit the mode button. If you scroll down to the fourth option, it's between radian and degree. And if you've never messed with it before, it probably defaulted to radians, which is what we're going to use here. So if we want to find the sine of pi over 3, you're going to hit the sine button on your calculator, having checked that you are in radians. And then pi is going to be second caret thingy divided by 3. And when I put in sine of pi over 3, I get 0.8660254, and we'll leave it like that for now. We're just going to say equals 0.866. Do the same thing. See if you can find the cosine and tangent of pi over 3 in your calculator. Okay, so if you put those into your calculator correctly, you should have gotten that cosine is 1/2 and tangent was something like 1.73. And this is actually one of the special right triangles that I think you went over with Miss Mansour last week, because pi over 3 radians does equal 60 degrees. So really that 0.1.73, that is the square root of 3, and 0.866 whatever is the square root of 3 over 2. And remember what that actually means. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent, SOHCAHTOA. Excuse me. And so if we take this angle pi over 3 and we draw a right triangle around it, then whatever value these lines have, however long they are, if this is the angle, it doesn't matter. The opposite side over the hypotenuse, that division, that ratio, will give you the square root of 3 over 2. And the adjacent side divided by the hypotenuse will always give you 1/2. And the opposite divided by the adjacent will always give you the square root of 3. And that is what those ratios mean. So one cool proof that you can do, this doesn't super fit in here, but I wanted to tell it to you because you need to know it later, is let's just quickly simplify sine of x divided by cosine of x. So what that means is sine is the opposite over hypotenuse over cosine is the adjacent over the hypotenuse. And we're using those letters to stand for the lengths of sides of a triangle, right? So we've got a fraction divided by a fraction. What do we do when we're dividing a fraction by a fraction? Keep, change, flip. We're going to keep our opposite over hypotenuse. We're going to change from division to multiplication. And we are going to flip adjacent over hypotenuse to be hypotenuse over adjacent. So then we've got, I'm going to erase this if that's okay. So we've got opposite over hypotenuse times hypotenuse over adjacent. And when we multiply fractions, it is just top times top, bottom times bottom. So we've got O times H over H times A. And we can simplify that because we've got an H divided by an H, and they cancel. And so we're left with just opposite over adjacent side. Hey, what trig ratio is opposite over adjacent? Sine x divided by cosine of x equals tangent of x. So that is another thing that you can use to find trig ratios. And let's get back to that aim for today's lesson, because boy, we are running out of time. How does it help us to conceptualize angles on the coordinate plane? Why did we bother to put our angles in standard form? So we've got an angle theta drawn on the diagram to the left. We don't know what that angle is, but we can say that it is hitting a point on the circle 12, 5. And here's what we can do with that. I'm just going to draw a right triangle in around this angle. And if I'm hitting the point 12, 5, that tells me that my x value is 12, which means I have gone over 12 horizontally, and then my y value is 5, which means I have gone up 5, which means that I know two sides of this triangle because of having it on the coordinate plane. I know that I've got a side that is 12, and I know I've got a side that is 5. And the side I'm missing is the hypotenuse. So let's just quickly find that, and then it will be really easy to find any trig ratio we want. And if we know two sides of a triangle and we want to find the third side, what are we going to use? Bam, Pythagorean theorem. A squared plus b squared equals c squared. The c is the hypotenuse, so that's what we're solving for. So we're doing 12 squared plus 5 squared equals the hypotenuse squared. So that's 144 plus 25 equals the hypotenuse squared. And that's 169 equals the hypotenuse squared. We need to take the square root of both sides, and the square root of 169 is 13. So the hypotenuse equals 13. And now we have all three sides of that right triangle, and sine is going to be the opposite over the hypotenuse. So what is sine? 5 over 13, because that 5 is opposite of our marked angle. Secant. Secant is the reciprocal angle of cosine. So cosine is adjacent over hypotenuse. Secant is going to be hypotenuse over adjacent. So the secant is going to be 13 over 12. And then cotangent, what is cotangent the reciprocal ratio of? Yep, of tangent. So tangent is opposite over adjacent. Cotangent is adjacent over opposite. So we're going to have 12 over 5. All right, guys, you have a Delta Math to practice. Feel free to email me or Miss Mansour with any questions you have, or if you are Miss Kaufman's student, feel free to email Miss Kaufman. All right, we love you, and we hope we'll see you soon. Oh, and it's Monday, so don't forget we have office hours this afternoon. Bye.